I decided to do a two-part series on the geometric derivation of the ellipse. The reason why I'm breaking it down is because the derivation is way more complicated than the parabola one and requires a lot more hairy algebra and tedious algebra. So I'll be proving the standard equation of the ellipse. Now, the first step into proving / deriving the equation is to state the geometric definition of the ellipse. Now, the ellipse is the locus of all points in which the sum of the distances from two given points called the foci are always constant. So what I mean by this, imagine we have like a horizontally stretched out ellipse, and we were to classify 2 points as the foci, and then pick two arbitrary points on this locus, like point P and point Z, and then connect segments from the foci to these arbitrary points. We would have the equivalent statement of F1P plus F2P is equal to F1Z plus F2Z. So that's what the geometric definition states. So now, for the derivation process, what I'm going to do is I'm going to draw the same ellipse like I did last time, and this time I'm going to assign it more coordinates. So I'm going to call this coordinate, points. I'm going to call this point A, this point B, this point C, and this point D. And then I'm going to call E the center of the ellipse, and I'm going to pick an arbitrary point on this locus, Z, and I'm going to assign it foci 1 here and foci 2 over here. Now I'm going to assign these points with their respective coordinates in a counterclockwise formation. So for point C, I'm going to give it coordinates of 0, B. Then for point A, I'm going to give it coordinates of -a, 0. Then for focus 1, I'm going to give it coordinates of -c, 0. And then for Z, the arbitrary point, I'll give it coordinates of x, y. Point D, I'm going to give it coordinates of 0, B. And then I'm going to give focus 2 coordinates of c, 0. And then for point B, I'm going to give it coordinates of a, 0. And it's good to know that the center is essentially the midpoint from the distance from focus 1 and focus 2, and the midpoint from distance A to distance B, and then the midpoint of CD. So basically, E is the midpoint of this and this. So E is the center of the ellipse. E is the center. Now, the second step of the derivation, since we've defined the coordinates, the second step will be to prove that the constant sum is the major axis. Now, the length of the major axis. What is the major axis? The major axis of an ellipse is essentially the longest diameter of the ellipse. But since the foci lie on the x-axis, we know that AB is greater than CD, meaning that AB is the major axis. So how do we find the major axis? Well, we know that the distance from A to point B is going to give us the length of the major axis. So, looking at our coordinates, we have to find the distance from -a, 0 and a, 0. And that's going to equal 2a. Now, how do we prove that this is the length of the constant sum? Or 2a is equal to the constant sum. How do we prove for that? Well, remember when I said these two segments were equal and these two segments were equal? Well, if we were to pick the arbitrary point A, and draw segments from F2 to A and F1 to A, we would have, by definition, the constant sum is F1A plus F2A. But since E is the center of this ellipse, F1A plus F2A, which is equal to the constant sum, is really equal to the entire major axis because E is the center of the ellipse. So we know that this is equal to the length of the major axis. Well, what is the length of the major axis? The length of the major axis is 2a. So we've proven that the constant sum is equal to the length of the major axis, or 2 times a. Now, the other relationship I want to prove is the fact that c squared is equal to a squared minus b squared. Now, you guys are probably thinking, doesn't Pythagoras' theorem state that c squared is equal to a squared plus b squared? Well, that's not the case. In this case, the a will be the hypotenuse. And the reason for that is, imagine if we drew from the foci to point C, we're going to get two equal triangles because we know that this segment is equal and then this segment is also equal, and this is perpendicular, so these triangles are congruent by Legge theorem, right? So since we know that these triangles are congruent by Legge theorem, then this segment, the hypotenuse, must be A, and this must be A. Because we know that F1C plus F2C is equal to the constant sum, right? Because basically the constant sum is when we just pick any arbitrary point and draw segments of the foci and add them up. So in this case, since these two triangles are equal, that means each of them will get length A and length A. Now, to find the this segment from foci 1 to point E, we use the distance formula. So foci 1 is coordinates of negative C0, and E is just center, or coordinates of 0, 0, meaning that this length is C, and C is 0, B, so this length is B, and this length is also C since they're congruent. So now, using Pythagoras' theorem, you get that A squared is equal to B squared minus C squared, plus C squared, not minus C squared. So we get that A squared is equal to B squared minus C squared. Therefore, we get that C squared is equal to A squared minus B squared. So we have proved the relationship. And this will become very useful as we do the hairy algebra. You'll see how useful this is. It's actually at the very end of the proof where this relationship becomes very useful. So now, how do we actually set up the algebra for this? Well, this is where the arbitrary point comes in handy. So we know that if we connect the two foci to the arbitrary point Z, right, if you connect these, we're going to get that F1Z plus F2Z is equal to the constant sum, or CS, which is equal to 2A. So since we know that the distance from the foci 1 to Z plus the distance from focus 2 to Z is equal to the constant sum, we can essentially just use the distance formula to rewrite this expression. So what is the distance from F1 to Z? Well, we know that F1 has coordinates of negative C, 0, and Z has coordinates of X, Y. Using the distance formula, we say that F1Z is equal to X plus C quantity squared plus Y squared. Now, what is the distance from focus 2 to Z? Well, we know that focus 2 has coordinates of C, 0, and the arbitrary point Z has coordinates of X, Y. Using the distance formula, we know that the distance is the square root of X minus C quantity squared plus Y squared. And all of this is equal to the constant sum, right? Because we've drawn two segments from the foci to an arbitrary point on the locus. Therefore, this is equal to the constant sum. Now, this is where we're going to stop at from part 1. Now, if you're very, very passionate about math, I recommend you get this equation into the form of x squared over a squared plus y squared over b squared, which is equal to 1, right? This is the type of equation we're trying to get this radical in. This whole expression is, we're trying to turn this into this. And that's what we're going to do in part 2. Thank you for watching. And in part 2, we're going to be doing a lot of algebra, so stay tuned.